In this lecture, we illustrate an example of an application of the bisection method with the software Mathematica. The bisection method is a numerical or approximation method for finding the solution of the equation f of x equals 0. F of x in this lecture is equal to minus x squared plus e to the x power. One can check that f of minus 1 is approximately minus 0.6 and that f of 0 is exactly 1. So that we have two values with y values that have opposite signs. This is the first of two conditions that, when satisfied by the function f, leads to guaranteed convergence of the bisection method to a solution of the equation f of x equals 0. The function f is also continuous everywhere. Continuity is the second of the two conditions that guarantee convergence to a solution of f of x equals 0. The viewer can show as an exercise that f prime is greater than 0 everywhere, and because f prime is greater than 0 everywhere, f is a strictly increasing function so that f must have exactly one solution to the equation f of x equals 0. Let this unique solution be x equals r. To get started with Mathematica, we first define the function. F of x equals minus x squared plus e to the x power. Then we define the endpoints of the interval on which we carry out the search for the solution. With the aid of a graph, we can choose an interval whose endpoints are very, very close to the exact solution. This can result in few iterations with the bisection method. For this example, we set the left endpoint a sub 1 equal to minus 1 and the right endpoint b sub 1 equal to 0. Since the bisection method involves steps or iterations that are repeated, we use a do loop. Within this do loop is a set of commands that we carry out at each iteration, and so we start with an opening curly bracket. First, we define the midpoint estimate c sub n at the nth iteration. C sub n equals half, or 0.5 times the sum of a sub n and b sub n. The next command defines the new interval whose midpoint will be the next midpoint estimate. This command involves a decision involving the sign of f of a sub n times f of c sub n. And so the command is an if-then-else command. If the product of f of a sub n and f of c sub n is less than or equal to 0, then we continue our search on the interval from a sub n to c sub n. This involves two commands, and these are for defining the left and right endpoints of the new interval. And so within this if-then-else command, we have another opening curly bracket. The new left endpoint a sub n plus 1 will be a sub n, and the new right endpoint b sub n plus 1 will be c sub n. Otherwise, if this inequality happens to be untrue, we choose the interval from c sub n to b sub n. We have another opening curly bracket, and the left endpoint a sub n plus 1 will be c sub n, and the new right endpoint b sub n plus 1 will be b sub n. We can insert a print command right here in order for us to see the result of each iteration. We are going to print a sub n, b sub n, and c sub n as a set of coordinates. We are also going to print the iteration number n as a fourth coordinate. This is the last command within the do loop, and so we type a closing curly bracket. And now we specify how many iterations we are going to carry out. If x equals r is the unique solution to the equation f of x equals 0, then the absolute error in using c sub n as the estimate for x equals r is given by the absolute value of r minus c sub n. And this is less than or equal to the absolute value of b sub 1 minus a sub 1 divided by 2 raised to the nth power. B sub 1 minus a sub 1 equals 1, so that the absolute value of r minus c sub n is less than or equal to 1 divided by 2 raised to the nth power. 1 divided by 2 to the 10th power equals 1 divided by 1024, which is less than 1/1000, which is the prescribed accuracy for the estimate that we are looking for. So we carry out 10 iterations, and therefore n goes from 1 to 10. We execute this entire cell of lines of code. And here we have the results of the iterations. The length of the interval from a sub 10 to b sub 10 is less than 1 divided by 500, or 0.002. Since r is also inside the interval from a sub 10 to b sub 10, the midpoint estimate c sub 10, which is minus 0.704102 up to 6 significant digits, has to be within 1/1000 of x equals r.